Hi everyone, in this video we can discuss some previous questions of GATE based on the topic floating point number representation. So before starting the discussion of previous questions, we need to understand some basic idea about the floating point number representation in binary format. We have certain standard for representing the floating point numbers in binary format like this IEEE 754 binary floating point number representation using single precision format and double precision format. I have already done one video for explaining this particular topic. The description of that video is provided in the description, also in the I button. If we need more explanation, you can watch that video after that trying to solve the questions. And here it is, just an overview of this single precision and double precision representation of binary floating point numbers. Okay, normally a floating point number is represented like this: whole part, decimal point, fraction. Right? The same can be represented in another way like this: 1.0 into 2 to the power minus 13, which is exactly matching with this particular number. And this is again the normalized form of this representation. And its general representation is thus: sine mandisa into, we need to represent the sign of the number first, then mandisa into base power exponent. Along with the exponent, we need to specify the sign. So based on this general format, here we have this particular representation for this number. How can we convert this into this form? For that, we need to shift this fraction point towards right and keep a single one to the whole part. After that, we need to represent all other fractions. So, shift this decimal 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. After shifting this point, decimal point, towards right 13th position, we get this whole part as single one. Single 1 dot 0 into 2 to the power minus 30. Okay, we need to specify the sign of our exponent. Okay, that means we need to divide 1.0 divided by 2 to the power 13 is equal to this fraction. Okay, that is why this is represented as 1.0 into 2 to the power minus 30. Sometimes you get confused regarding the sign of exponent. No need to worry about this. If we shifted towards right, then simply put a negative sign. If we shifted towards left, then the exponent will be positive. Okay, so just keep this point in your mind. If we shifted this decimal point towards right, then we need a negative exponent. We need to put a negative sign for the exponent. The exponent actually indicate number of shift towards right. And if we shift towards left, then the exponent will be positive. Okay, and in this single precision format, this is actually a 32-bit representation. The first single MSB bit is taken as the sign bit. Next coming 8 bits from the MSB side. It is the exponent part. The exponent is represented in the biased exponent form. And the remaining 23 bits used for representing the mantissa. Okay, consider one example, 85.125. This is a decimal number. We need to represent this in single precision binary floating point format. For that, we need to convert this into binary form first. So 85 is converted and we get a binary representation for 85 like this. Next, point 1 to 5. We need to convert into binary. We get a binary equivalent like this, 0.001. So 85.125 is actually equal to 1010101.001. Now this binary form we need to make in this particular form. That is 1 point fractional part into 2 to the power exponent form. Okay, so for making whole part as a single one, in which direction we need to shift this decimal point? Here in this example, we need to shift towards left in order to make this decimal point here. So while shifting, how many position towards left? 1, 2, 3, 4, 5, 6. So this become 1.0101010001 into 2 to the power 6. So this is the normalized representation of this particular binary fraction form. And 85.125, it is clear that this is a positive number. So the sign is taken as 0. So from this format, it is clear that here it is the exponent part. We need to store the biased exponent. How to convert the exponent to biased form? We need to add the bias value with the given exponent. Here the exponent is actually 6, positive 6. With that positive 6, in the single precision format, the bias is 127. So while adding this bias value 127 with the actual exponent positive 6, we get a biased exponent as 133. Its binary is thus. Okay, so now we can put everything in this format. Sign bit is 0. 0 is put here in the first MSB bit position. Next, we need the exponent part. The biased exponent part. How many bits are used here for representing the biased exponent? 8 bits. Here, this representation actually contains 8 bits. So, directly write this value here, 100000101. And we need 23-bit representation for normalized mantissa. In the normalized form, the mantissa is thus 01010101. But this is not actually not contain 23 bits. So we can write this, and the remaining bits we can append different number of zeros in order to make this field full of 23. Okay, so after that we can convert this into its hexadecimal representation. How? By grouping these bits from right hand towards left. We can make different groups of 4 bit and assign its hexadecimal equivalent. First 4 bit is 0, so its hexadecimal equivalent is 0. Next 4 bit is again 0, hexadecimal equivalent is 0. Next 4 bit is again 0, its hexadecimal equivalent is 0. Next is 0100. 0100 is hexadecimal 4. Right. Next is 1010. 1010 in hexadecimal as A. Again 1010. Again A. Next is 0010. 0010 is 2. Next is 0100 again 4. So this is the hexadecimal representation corresponding to this single precision format of this decimal number 85.125. The same method we can apply for the double precision format representation also, but here the field bits are different. For representing the sign bit, here again use a single MSB bit. So double precision format is actually using total 64-bit representation. Single precision format is actually 32-bit representation. This is actually 64-bit representation. 64-bit representation, 0 to 63 total. They must be single bit. That is, the 63rd bit is the sign bit. Next 11 bit for biased exponent. Next 52 bit for our normalized mantissa. So the same number with its binary format. Now the second step is normalization. So while normalizing, we get this 1.01010101 into 2 to the power positive 6 normalized form. And biased exponent is obtained by adding the bias value 1023 here with the actual exponent 6. In double precision format, the bias value is 1023, and single precision format, the bias value is 127. So for getting the bias exponent for this particular field, add bias value 1023 with this exponent 6. So this is the biased exponent 1029, and its binary is 10000000101. Okay, now we can follow this. This is a positive number, so the sign bit is 0. If it is negative, then sign bit become 1. Next is exponent. We need 11-bit representation. This is actually in 11-bit. So we can directly write this biased exponent in its binary form here. Next is mantissa. We need to take the mantissa from the normalized form. Normalized form always contains a single one in the whole part, and all others comes after this decimal point. This particular representation is actually considered as the normalized form, 1-point form. Okay, from this normalized form, we can consider this fraction as the mantissa, but this is not in 23-bit representation. So, remaining bit, we can append different number of 0 to make this entire field as 52. Here we need the mantissa in 52 representation. So first write this one as it is here. After that, in order to make this representation in 50-bit form, append remaining bit with full of zeros. Now we can group these, and each group contains 4 bits and assign its hexadecimal equivalent, and we get an hexadecimal equivalent for this particular number as thus. Okay, so now we can consider some questions. So the first question is, the decimal value 0.5 in IEEE single precision format has dash fractional bits, and which is the exponent value. This is the question. Decimal value 0.5 is given and is positive. It's IEEE single precision format we need to get, and from that we need to identify how many or which is the fractional part and which is the exponent. So just look at this format. This is a single precision format, 32-bit representation. M must be single bit sign. Next 8-bit form the biased exponent. Next 23-bit form the normalized mantissa. So based on that, take this 0.5. This 0.5, how can we convert it into binary? For converting a fractional decimal number into its binary, we need to multiply that number using 2 continuously. So first multiply this 0.5 using 2. 0.5 into 2, we get 1.0. So keep this 1 here and consider the fraction. The fractional part again multiply with 2 again. The base value 2. Again we get 0.0. So we can continue this procedure up to n number of steps in order to get n fractional bits. But actually in this particular case, In the first multiplication itself, the fraction become full of 0. So now we can directly stop from this first step itself. And which is the binary equivalent of 0.5? That is the whole part. We need to arrange the whole part from top to bottom in order. So 0.5 in decimal 10 is equivalent to 0.10. We need to arrange this whole part of each and every multiplication in top to down manner. So 0.10000, which is in binary, is equivalent to 0.5 in decimal. So 0.10 in binary is equivalent to 0.5 in decimal. Now we need to normalize this. How to normalize this? Normalized form contain a whole part with a single one. So make this as one point form. Shift this decimal from this position to this. We need a single shift towards right. So the normalized form is 1.0 into 2 to the power. How many position actually shifted? Single position. And towards right, so put a minus sign. So 1.0 into 2 to the power minus 1. Okay, so now we can consider this option. So from this step, that is after the normalization, we can directly choose one correct option. From this it is clear that the fraction contains full of zeros, 23 full of 0 bits. So option A or B, from these two, one among these two is the right answer. And the exponent is minus 1. And the exponent is minus 1. The options are given with the exponent value, not the biased exponent. Right? So, fractions with 23 full of zeros and exponent is minus 1. So, the option B is the right answer. Second question. This is again a floating point number representation. The question is based on the floating point number representation, but it's not based on single precision or double precision format. Here, the representation is directly given in the question. Total 16-bit representation is given. First bit, the MSB bit, single bit, 15th bit is taken as the sign bit. For 8 to 14, 7-bit is used for the biased exponent. The bias value is directly given here with 64 as the bias. And the remaining 8-bit 0 to 7 is considered as the mantissa. Now consider the question. Consider the following floating point format. The mantissa is a fewer fraction in single magnitude form. The decimal number 0.239 into 2 to the power 13 has the following hexadecimal representation. The options are given in the hexadecimal form. Here, we don't want to consider normalization and any rounding operation. That means simply convert this into its binary form and put the exponent part as well as the mantissa in this, without doing any normalization. Normalization means one point form. We don't want to consider that one point form here. Simply convert this into its binary and directly put the values here. And one more thing, here we need an exponent, biased exponent. The bias value is 64. So whatever exponent we obtained, to that exponent we need to add bias value 64 here. So first we can convert this into its binary. How? 0.239 into 2 is 0.478. The whole part is kept here as a base. Then multiply the fraction again using 2. Then get 0.956. Whole part is kept as here and consider the fraction. The fraction is multiplied again using 2 and repeated here total 8 times. Okay, we can repeat this different number of times, but here we need 7-bit representation, so repeated here 7 times. And arrange this all part from top to down in order to get the equivalent binary format 00111101. So this is the binary equivalent of 0.239, that is 0.00111101. Okay, so this is the method for converting a decimal fraction into its binary equivalent form. Here we can stop here we don't need any normalization. Okay, so here the exponent is actually in the question itself 0.239 into 2 to the power 13. The exponent is actually 13. Positive 13 is given here. We need to make it in its biased form by adding this bias value 64. So we get 77 after this addition. Convert this 77 in its binary form. This is not a fraction, so continuously divide using 2, base value 2, and get this binary form like 1001101, which is the binary equivalent of decimal 77. Now we can combine all these values together and write like this. This is the sign bit 0, then 7-bit biased exponent like 1001101, 7-bit representation. Next is 8-bit mantissa 00111101. Okay, now we can group this from right to left and assign for different group its equivalent hexadecimal form. So this 4 bit is equivalent to D. Next 0111 is equivalent 0011 equivalent to 3. Next 1101 again equivalent to D. 0100 equivalent to 4. So which option is the right answer? D. Okay. So the same question, next is the same question with some modification. Here we need the normalized representation for the above format. The mantissa has an implicit 1 preceding the radix point. That means the explanation for the normalized representation is directly given here. Normalized form means the mantissa has an implicit 1 preceding the radix, that decimal point. Okay, and we can append any number of 0 in the mantissa field in order to make this as 8-bit representation. Okay, so we need this floating point representation in binary form for this number 0.239 into 2 to the power 13, and the options are given in its hexadecimal representation. The same, while converting this into its binary form, we get this value. Here we need normalization. So our next step is making this as 1-point format. So for getting a 1-point format, how many shifting are needed? 1, 2, 3. 3 position towards right. So the normalized form is 1.11101 into 2 to the power, how many shift? 3 shift towards right, so 2 to the power minus 3. Already we have this exponent here, 2 to the power 13, and now we get 2 to the power minus 3. Okay, so normalized form is 1.11101 into 2 to the power minus 3 into 2 to the power 13. That is this binary form into 2 to the power 10. In order to get the biased exponent, we need to add this exponent with 64, because this is the x64 representation, right? So we get the biased exponent as 74. Convert this 74 in its binary form, and we get a binary representation for the 74 like this: 1001010. Okay, now we can consider the representation. Sign with bit single 0 because this is a positive number. And biased exponent is 1001010, again a 7-bit representation included in this biased exponent part. And the normalized mantissa is 11101. This is actually 5-bit form, but we need total 8-bit mantissa. So we can append 3 more 0 to the right hand in order to make this form, or in order to make this mantissa field with 8-bit. Okay, so the options are given with hexadecimal representation. So make different group and assign its hexadecimal equivalent. This last 4-bit 1000 is 8, 1110 is E, 1010 is A, next 0100 is 4. So which is the right hand option? Option D, 4AE8. Okay, so in our next video we can discuss some more questions based on the floating point number representation. Thank you.